Okay, let's go to our presentation. I'll move that out of the way. So, good afternoon, everybody. First of all, my name is Greg Milliken. I am the CEO of the Engineering Link Group. It's a very grandiose title for an operation of one. There used to be two of us, but Paul has retired and is actually battling some cancer at the moment. So he is taking a very big backseat while he looks after his own health. But at 83 years old, he's most certainly deserved that. So I'm pretty much running the situation at the moment with Paul watching over my shoulder like a hawk. So welcome to this webinar. We're very grateful that you've given up your Wednesday afternoon. My apologies, there is an ambulance going past my school currently, which you can probably hear in the background. So today I'd like to first of all acknowledge the Engineering Link Group, the Queensland Government, Engineers Australia, acknowledge the Turrbal, Yagara and Gobi Gobi people, which is where I'm currently situated right at the moment. And I'd also like to acknowledge the Wulgurukaba people as where I was born, up in North Queensland in Townsville, as First Nations owners of the lands where we meet today. We repay respect to their elders, laws, customs and their creation spirits. We recognise that these lands have been and has always been places of teaching, research and learning. Engineering Link Group acknowledges the important role Aboriginal and Torres Strait Islander people play with our engineering community. So, as I mentioned, we started, to those who haven't had any involvement in our organisation, we started in 1994. I am originally from Townsville, as I mentioned, worked at Barangay State High School and Townsville State High School for many, many years before moving here to Brisbane. And we started doing this way back then, and it's grown and evolved and changed and developed over the last 32 years to where we are today. Our whole purpose is to try and provide support for teachers and their students, and engineering was the path that led us to do that, and we've been doing it for a long time now and have the privilege of getting to meet and work with thousands of engineers over the years. I'm not an engineer. I never professed to being one. I'm a teacher, as I mentioned. I've been working for a long time now. As I said, I'm currently curriculum leader here at St Anthony's College in Burpengary for mathematics. I have been a maths head in Townsville, and I've been a CL of Science here at school as well. As I mentioned, the engineering group was formed with Paul way back in 1994. So yeah, we've been around for a bit. So what is the competition? We've been operating the competition since 2014 with the support of the Queensland Government. It was originally a TEAS operation. So we've had well over 3,700 students and lots of different schools across Queensland participate in this event. And we're very grateful to be sponsored by the Queensland Government, by QUT, and of course by Engineers Australia. And they've been on board with us for quite a few years now, and we're very, very grateful for that support. I'm going to introduce Mike and Natasha in just a moment, but they are our experts. As I mentioned, I'm not an engineer, so I'm by no stretch of the imagination an expert. While I do have a bit of, I know more about bridges and spaghetti than I probably care to ever think I would. However, they are the people that have most information. So Mike's going to present to you in a moment about the physics engineering bridges and gives you lots of tips about that. And then I'll get into the actual competition and information about the competition towards the end, and then I'll open it up at the end for questions. As I mentioned, this is recorded, and this recording will be made available along with the presentations via our website, and I'll email that link out once it's uploaded and ready to go. So, with no further ado, I'd like to introduce both Mike and Natasha. I'll introduce Natasha first. So Natasha is a principal engineer in TMR's Engineering and Technology Structures team with over 12 years experience in infrastructure design, construction and project management. She has previously worked as a construction engineer on several large-scale infrastructure projects, overseeing the delivery of the complex structures, including bridges, retaining walls, marine jetties, ferry terminals and structural concrete works, supporting LNG facilities. One of the things Natasha enjoys most about bridge engineering is seeing a project progress from design drawings to a structure that people can walk or drive across every day. connecting communities and improving how people travel. She's passionate about encouraging students to consider engineering as a career and showing how maths and science are applied in real-world construction projects. We're very grateful for Natasha to be on board today, but the person you're going to hear most from is Mike. And Mike has been very kind enough to donate his time and expertise for a number of years now. But Mike is a director, Mike Whitehead is a director in TMR's Engineering and Technology Structures team also, with over 43 years experience in road design and structures. He's a chartered and registered professional engineer. Mike has been with TMR for his entire career and involved in a wide range of projects from simple rural roads to major motorways. Key activities have been design, vehicle dynamics, engineering materials, research, development of departmental policy, standard specifications and manuals, as well as training development and delivery. He has also participated at national level with Ausroads in the development of national road design guidelines. Mike is keen to encourage others to be interested in engineering and help develop young engineers. He's been a sessional lecturer in engineering at QUT for over 10 years, and I'm very, very grateful to both of them for their time and expertise. I am going to stop sharing and stop talking.
That means it's my turn. Okay. Hang on. Can you all see that? I can't hear anything, sorry. All right, so thank you for attending today. I'm hoping to be able to just sort of run
Mike,
through
I can't see it, mate. I can't see it at the moment. I can only see you.
Okay. Let's go share. That might be better.
That's better. I've got your Teams invite. There it is. There we go. Got it, mate.
There we go. Apologies for that, everyone. Still getting
Okay.
used to technology, even though I've been doing it for years. All right. Well, thank you again for attending today. So the session I'm going to run through now is really talking about some of the basics of bridges, keep it nice and simple, but hopefully help give you all a better understanding of just what's going on in a bridge structure and how it applies to the spaghetti bridges that the students are going to try and design and develop. And hopefully this guidance will help get them to build successful bridges, ones that don't collapse virtually straight away. That, you know, it gives them a bit of excitement to see them actually carry some load. So we're going to look at the forces involved. Everything in engineering basically has forces involved. So we need to understand them so that we can design for them and then get our materials and structures to handle them. We're going to look at some of the types of bridges and which ones in particular will probably lead to some successful structures in spaghetti bridges, and then look at that practical application to this particular project. So looking at forces first up. So when you consider a bridge, we need to understand that the forces involved and to be able to handle them. Now, forces can be both static, which is the stationary forces, they don't move, or dynamic forces, which are obviously the moving ones. For this project, luckily, we only look at the static ones. We actually don't have live loads or anything like that running across the bridge or dealing with water, wind, or anything like that. So the bridge itself, it supports itself. It's a dead load. So it needs to be able to cater for that, and that's why we have weight restrictions on these structures. It carries a load, which is generally what we call a live load. In this case, the load will be just a single point load and will be pulled down. So yes, it is live as it's increasing, but it's not moving and dynamic across the structure itself. And then it's got to transfer all of those loads to the ground, because it's the ground that actually holds the structure up in the air. In this case, it'll be the test rigs supports on either side. So when we look at the forces that we're talking about, they're the 5 main ones, key ones that basically all structures have to deal with. So when we're looking at the compression forces, they're the forces that will squeeze or push the members together, and essentially the member will try to react and it'll try to buckle, bend away. So the way we can best resist compressive forces is increase the thickness. Now what we can do with the spaghetti is, obviously the spaghetti itself is restricted to its size that it's manufactured at, but if we can put a number of them together, that then increases the thickness. Under tension, that's where they're being stretched, being pulled apart. Ultimately, it snaps. Not much we can do about that. But yes, that's the way that one handles. Now again, a couple of strings of spaghetti glued together will increase the capacity to resist the tension. And then you've got the bending. And bending is where multiple forces occur. So to help explain that, let's have a look at a simple beam. So we've got here a simple beam. The force P is pushing down right in the middle. For the spaghetti bridge, it'll actually be underneath pulling down, but it's the same result. And then you have the two supports RA, RB on either side holding the structure up. So when we have bending going on, you can obviously see the member there, the beam is actually bending down, and that's what's going to happen in a simple spaghetti bridge. Now, part of that is where you have that beam. If you can imagine a halfway line there where you can see those red dashed lines, the top part of that beam is actually in compression. So the members along the very top are being squeezed together. You can tell that because the shape of the bending, it's actually shortening it. So it's squeezing together. Whereas the ones under the bottom, they're in tension, they're being stretched. So a beam that's in bending is actually under compression and tension at the same time. And we can use that knowledge to our advantage, and I'll show you that soon. There's also shear going on. So when you've got a force pushing down one direction and the support's pushing up from the other direction, there will be a plane somewhere there, and they're usually out towards where the supports are for a beam, where it's just going to snap, and that's where the shear forces are. So in a spaghetti bridge, that's the sort of area that you might need to thicken up some of the structures to be able to handle that. And the last one is then torsion. Torsion is twisting. So a beam will try and twist when it's under extreme load, and it depends on the shape of the beam itself and where the loads are placed. Are they symmetrical, etc., or are they slightly off to one side? And that'll depend on which way the beam will twist and fail that way. So again, what we try to do is get a couple of beams side by side or shapes side by side, and then brace them together so they stop that torsion. So again, the main approach for this project is that the load is applied underneath to whatever the structure is on top, and then the supports will hold that up. Now, hopefully, if the load is applied in the middle and the structure is positioned, well enough on the test rig, the loads will roughly split half. So half's going one way, half's going the other. So the structure should be, when it's designed and made, should be symmetrical and mirror image on either side, so it's handling the loads in the same way. We have seen some structures in the past where they do something a bit different one side and a bit different to the other side, and so the loads then will split and transfer differently, and then the structure can behave in different ways. So now that we've looked at the basics of the forces that are involved in the structures, let's have a look at some of the different types of bridges that we can use. So these are the main types that you will see. You have beam bridges, then you have truss bridges, you have cantilever bridges, arch bridges, suspension bridges, and cable stay bridges. And you can see examples of all of those, in the southeast corner everywhere in Brisbane, and you can see some up in North Queensland. The beam bridge is obviously the simplest of all bridges. The truss has its benefits. It's a lot more complicated. Cantilever bridges are a unique not unique, too much of a term, but a bridge that basically just relies completely on the supports. You can just see a very faint line in the middle of that. What that means is the bridges can stay up. It's not relying on transfer loads right across from one side to the other. Each side is holding itself up. Something that a lot of people don't realise is the Story Bridge in Brisbane is actually classified as a cantilever bridge. And so what we mean there is if we could get a saw and cut the bridge perfectly in half, it would stay up, it won't fall down. So each support on each side of the river is holding the structure up. We then have our arch bridge, which is one of the oldest forms of bridges around, and then suspension bridges and cable stay bridges are sort of more recent versions, but they've also been around a lot more often. For the spaghetti bridge, the types of bridges that we're looking at is probably in the main, the beam bridge, the truss bridge, and the arch bridge. Unfortunately, that arch won't work, so we need to use that because one of the rules is we can't use the test rig, the sides of it for side support, so it's got to sit perfectly on top. So we just switch the arch to the top. So now let's have a look at some of the practical application of that. So the materials you're using is commercially available spaghetti. So you just go to the shop and you buy it. It's nothing too flash. And you can use glue, which is white glue or PVA glue, hot glue or super glue. We're not using resins or anything like that. It's just the simple glues. Dimensionally wise, the structure must include a loading hook at midpoint of the bridge. Greg will talk more about that later on. Must have a deck. Now the deck must be wide enough for a matchbox car to pretend to drive over it. So we're looking at a minimum width of around 3 centimetres for the deck. It's not a solid deck, so don't need to get a whole lot of spaghetti lined up on it. You can have gaps between it, so it's a lightweight deck because we're not actually physically driving a car across it, but it must look like it's a deck for a bridge. The bridge must span at least 37 centimetres with a clear span of 35 centimetres. So the 35 centimetres is the width between the test rig supports. If you only make it 37 centimetres, it means only a centimetre on each side is actually transferring the loads down. So some students make that a little bit bigger just so that they can get it adjusted and transfer that weight. No thrust support from the vertical sides of test rig can be used. So that's why I was saying with that diagram of the arch, it was pushing against the sides. We can't allow that, so you have to move the arch to the top. And the total mass of the bridge, including spaghetti, glue, and loading hook, must not exceed 300 grams. So what do we need to consider? So key factors to understand is how the spaghetti performs, and it's quite a good idea for the students to have a bit of a play and try it so they can see what's going on, do some experiments. So what does it do under under compression? So, I mean, if you get a piece of spaghetti and put your fingers on either end and push them together, you'll see it bow very, very quickly. But obviously, if you can glue 5 or 6 pieces together and try to do it again, it won't bow as easy. So therefore, it's handling those compressive forces much better. Under tension, again, you can then hold a piece of spaghetti and then load it from the other side and see how much weight it can carry before it snaps. So that's it under tension. Obviously trying it when it is actually glued. So you could try a piece of spaghetti that how it performs dry and then glue it, let it dry and see if it changes it. So we have heard of some instances where people have used a lot of like PVA glue and it can weaken spaghetti and rely more on the glue itself. So, and can you bend it? Can you not bend it? So test it when it's being glued and of course when it's wetted. So you'll see some of the shapes that we've got that come up, particularly with the arches, where students in the past have made little rigs for themselves. They've wet the spaghetti to then be able to bend it into the arch shape, but then it's got to dry. Now, does that change the properties of the spaghetti? It's good to experiment to try it out. It's also a good idea, particularly because it's not terribly expensive to buy the spaghetti, but to do their designs, to actually build the designs and then to try and test it to see how much weight it can carry. Is it going to twist? Is it going to buckle? Is it going to collapse quite quickly? So prototype the designs, test it and see how they go. Also be aware that the quality of spaghetti varies from brand to brand. So they're not all the same, and also between packets of the same brand. So you might get a weaker set out of one brand at one packet compared to the same brand from another packet where it seems to break a lot easier. So it's fun stuff to use. So how the metal hook is supported, this is critical. So again, the metal hook, apart from the hook where we connect the test rig to, it's got a little plate. So the idea is that plate is what holds the hook to the spaghetti bridge. So the students have to think about how they're going to support that and give it as much strength in there, because that plate is obviously going to pull through the spaghetti and fall out of the bottom. So to be able to transfer the loads to the sides, it needs to be put into the structure quite well. So try and utilize the whole plate area to transfer the load, not just sort of the edges, and it'll pull through quite easily if we do that. As I said, the deck doesn't need to carry any load to keep it lightweight. Bracing is also important to help keep the structure from twisting. So again, instead of just looking at a simple, say, a beam and make it as big as possible to carry the weight, the simple beams will try and twist. So what we suggest is to get a couple of them together, brace them up so that they stop the twisting. Now, if you go down the path of looking at a truss bridge, there are several trusses around. Google them and you'll see all sorts of different ones will pop up. The typical ones are what we call the Pratt truss and the Warren truss, and it's just the way they perform and the way they have their members put together. What we've done here is typically with a load applied in the middle, which is similar to what we'll do with the spaghetti bridge. We've coloured the members that will be in tension and coloured the members which will be in compression. So in these instances, if we go for a truss of this type, what we'd be looking at is making the blue ones thicker than the ones in red, just so that we can handle those forces. Here's another diagram of a truss bridge. Now this one just shows you the detail. You wouldn't need to go into that for a spaghetti bridge, but it does give you an idea of all the bracing that goes on. So apart from the deck, which carries a lot of the load, that deck load or the loading of the deck goes up into the truss, and the truss then transfers it to either side of the structure. So you can see there the different members that are available, and you'll also see the cross bracing going on again to help with the twisting issues. A great example of a truss bridge for those up in North Queensland is the Burdekin Bridge. So it's one great big long truss, but each component is very similar to the next from one pier to the next. Then we move on to arches. So arches are a little bit different. So the normal arch, which is pictured in this diagram, is you'll have your stiffening girder or your deck where the loads are applied. Then we use vertical hangers to take the loads up into the arch, and then the arch transfers under compression to the supports on the either side. So that's a normal arch that we would have. With spaghetti bridges, and there's a picture of one in the right-hand top corner there, and you'll see them if you do some Google searches. Because the load is being applied in the center, the vertical hangers are no longer vertical. They actually will radiate out from that. The idea of that is so that the load is taken straight into the arch, by virtually all of the hangers that are being used. So that's one way of doing it. But again, the trick here is to get the arch as circular as possible. Obviously, the spaghetti has to be wet or dampened slightly to be able to bend like this. It doesn't have to be in much. Some brands are a little bit better at bending than others, but most of them will snap pretty quickly. So they do have to be dampened to be able to be bent around. And this usually requires the team to build a rig so that they can bend it around and hold it in place while it's drying, particularly once it's glued. There's a picture of an arch bridge in Brisbane. The hangers are a little bit different than straight vertical, but they're certainly not radial out from the center point. So beam bridges are simple structures. Beams or girders need to be thick or deep enough to resist the bending forces. And so a good example of that is if you've got a normal 30 centimeter ruler, put, say, a couple of pencils on the table and then just lay the ruler across those. If you put your finger on the middle, it'll bend very, very easily and you can touch the top of the desk without much effort at all. But if you could stand the ruler up on its edge and then try and push it down, you'll find it won't go. So the thickness in the direction of where the force is being applied is where it'll get its strength from. But again, because it's very thin and the ruler, it will twist quite quickly. So sometimes you need a bit of thickness in width to resist that. In beams, what we do for beam bridges, for example, we'll have a number of beams depending on the width, but then we'll have the cross bracing between the beams to stop again or to minimize that torsional twisting that could go on. So again, for a spaghetti bridge, you could use two beams, one either side. The deck will go across, and then just some cross bracing underneath to help it with the twisting could be sufficient. Now, there are many different types of beams available. So we have solid beams. You can have I girders, T girders, and you can have box. And they'll talk a little bit about those. So in a solid beam, what we've got here is the dots represent as, this is a cross section through the beam. The dots represent a piece of spaghetti. So we could give it some width, we can give it some height, we could glue them all together, let the glue set, and that gives you what's called a solid beam. So again, the depth improves the strength against bending. So you could do some testing to work out what will actually work or what will hold a fair bit. And then the width can resist the twisting. Now, if you put two beams side by side and some cross bracing, well, then the width doesn't have to be all in one beam. It can be shared across it. Now, what we do have is the two common variations that we can use. The I girder and the T girder. So what the benefits of these, if you look at the I girder, it's quite thick at the top. It's also quite thick at the bottom and thin in the middle. So again, if you go back to that earlier diagram when you've got a beam in bending, so the top part there would be under a lot of compression, and we know to resist compression you need to thicken it up. So that's where that top flange will benefit. The bottom flange for an I girder can help also if the beam is being bent in different directions. So what in the spaghetti bridge, because it's only being bent in one direction, a T girder is probably beneficial. So the top of the T gives you better strength in the compression side of things, where the bottom is in tension, so you don't need quite as thickness. The other thing to be aware of is overlapping the strands of spaghetti. So when you do a join, to help with this, what it can be is don't do the join down the middle like that's demonstrated there, because that's just relying purely on the glue. Now, it might be arguable the glue is stronger than the spaghetti, so it could work there. But you would be placing a couple of shear planes in there where the spaghetti is all lined up together. The best thing you could do is to try and overlap as best you can, so that there's no single join lines up with another single joint. So that spreads the shear planes out and hopefully give you a more potentially homogeneous girder or beam. So this is just a picture of a typical beam bridge that we build quite a lot of in Queensland. They're quite simple, they're cost effective, and they do a very good job. Here's the underside of a bridge. Not many people get underneath bridges and look up, but what you can see is a whole series of girders. There's 7 of them, and then you can see the cross bracing that goes between them that's spaced out. So that helps with the torsional twisting. The last one I'll talk about here for these bridges is what we call a box beam. Essentially, they're a big box, and the gateway, which is the picture from, is exactly that. Inside is hollow. So the benefit of this is instead of making a solid beam, they're getting the strength for bending from the depth. So it's quite high walls on the sides, and then the cross bracing is across the top and across the bottom. So yes, it's hollow. We've got people that can walk inside to do their inspections, etc., in the gateway, and we've got other. The Riverside Expressway's got hollow beams as well, where people can walk inside it to do their inspections. So there's different shapes there. The pictures on the left-hand side there can show you a number of shapes. But yeah, the students, I think, could build easily a simple box beam. The top would be your deck. The bottom would be part of your bracing and probably strong enough, particularly if you strengthen it around where the hook is. And then the sides could be quite deep, while giving you some strength. I'd like to see a box beam. I don't think I've seen one being built in my time with this project, but that's the one that would work there. And just to finish off, this is an old railway bridge. It was all timber once before, that we've come along and used a steel truss to give it some extra strength and improve safety. So this is a combined bridge where we've used a number of different methods to build it together. Now, don't expect the students to get stuck into that, but it's just an example of the different ways that engineering can be applied to solve various problems. So with the spaghetti bridges, again, I recommend the students, the teams, have a look on Google, have a look at different types of bridges, have a look at ones which are stronger. There's plenty of examples of past past competitions from various countries. The arches do seem to win out quite a lot, but they're also quite difficult to build. But it's can present a challenge. As I said, I think a box beam would be another successful design. We've got a lot of big bridges in around the world which are made of box beams, and they are very capable structures. Try not to get your students to build very thin bridges and that are very wide. They will collapse very, very quickly. So they do need to get some thickness in the vertical plane so that they've got some chance of holding up the weight that's applied, and gives them a chance to have a bit of a win, or at least do well in the competition. But that essentially is it from me. Back over to you, Greg.
Thanks, Mike. Turn on the right thing. Mike's covered a lot of the information specifically regarding the competition and the specification, so I'll probably cover some of those again, but I think it's important. So welcome to those of you who have never participated in the competition before, but I know there are some of you in the webinar that have done it before and are here for some tips and advice, which is obviously welcome. So if you are new to the competition, it's actually open to all grades from 5 up to 12. So if you're a P to 12 school or a 5 to 12 school, or have really good connections with your feeder schools, if you are a secondary, your primary feeders, then by all means, feel free to invite them to the competition. They are most welcome. We've had the youngest place getters we've ever had were grade 6s from a few years ago, which was pretty cool. They came third. Which is very exciting. So it doesn't matter how old, kids are still more than capable. You can have teams of up to 4. Individual students are most welcome just to design and build a bridge. Teams can nominate more than one bridge. They just have to give their bridge a different name so I can keep track of which bridge is which. But if they want to enter more than one bridge, they're most welcome to do so. Mike's talked about the bridge, the spaghetti and the glue, and I'll go into that in some detail in a moment. We test them all on the same rig, and you'll see some images of that shortly. And the way we decide the winner is we measure the largest peak load before the bridge fails, and I'll talk about what that looks like in a second. It is absolutely free to enter. No, it costs you nothing. If you've already expressed interest, you should have received your load hook. Pardon me, if you need more, then get in touch, please. I'll talk about where we're testing and when in a little while. And the competition is open now, and it can run until the 1st of September. All right, so this is an image of the load hook for those who haven't seen it before. It weighs around about 67 grams. So it's important that the students incorporate that weight into their bridge. So if you think that through, the actual spaghetti and glue is only going to weigh around 230 grams or so, because 67 grams is that load hook. You'll see that it has a plate. You can disconnect the plate to the ring, but they have to be together, and you can sort of see the approximate dimensions. The 30 mils is the minimum width of the bridge, which is where that comes from. It's the width of the plate, but you can put the plate either way around, whichever way you prefer. The ring itself is facing downwards, and you'll see why. For those who haven't seen the rig in a moment. Mike mentioned that you can have any type of spaghetti you want. They're just 2 photos that I've been able to find. You do not have to use those brands. You can use whatever brands you want, as long as that's spaghetti. There are different types of pastas, and they all look the same in some ways, but they're different sizes, different shapes. But as long as it's spaghetti and labelled as such, then it's fine. Different types of glues. Each of these glues have different strengths and limitations. Some schools, because of their risk assessments and so forth, don't allow different types of glues, and that's perfectly fine. You have to work with what you've got and what you're allowed to use if you're doing it at school. They're the 3 main glues that students have used, and with all the different levels of successes and depending on how they use them. What you're not allowed to use is liquid nails in any form, whether that be a caulking gun or in a tube like that, or Gorilla Glue or epoxy glue or anything that works of that nature. It's very, very difficult for us sometimes to know what kind of glue has been used. It's pretty obvious when it's Acrydia and hot glue, but sometimes the super glue and the epoxies can look a bit the same. There's no real way for me to test that, so it's more on a trust thing, to be honest with you. I really have to just trust that schools are doing the right thing. There have been occasions in the past where schools, it's been obvious that they've used the wrong glue, and I've had to disqualify them, unfortunately, which is nothing. It's very unpleasant conversation to have, I can tell you. So please encourage them to use the only glues that are allowed. If you're at all unsure and you want to check, please don't hesitate to send me an email and ask, or you can ask at the end of the session. So Mike's went through this really well, and so I'm not going to spend a huge amount of time on this. There are a heap of designs up on our YouTube page, including some videos and stuff you can have a look at. Try different glues, what works, what doesn't work. Depends on, again, on your circumstances and how much time you've got. Think about, like every good activity, all students want to do is just grab the spaghetti and the glue and start building, but try and encourage them where you can to actually do it a bit of design, have a think about what it might look like. Allow them to look at this. This video will be the recording of this will be up on YouTube and on our website. The students are encouraged to have a look at it, particularly the first part of it, to get those ideas and make their bridges as best they can. And I think it's really important that the load hook is in this as centered as possible. If you're sharing your load hook between different teams, just make sure that the whole is available so they can transfer the hook from one person to the next. But if you did want more than one hook, as I said, just get in touch. Someone sent me an email the other day and asked me, do I know of any designer websites that they could use or recommend to their students? And these are the two that people have used over the past. So I just thought I'd put them in this slide. Trosme and bridgedesigners.org. So if you have the capacity or the time to run through these with your students, or at least let them have a play with it, they are two that students and or teams have used in the past. So I'll just let you know about those. These are some photos of a bridge that a student who built about 10 years ago now, so they're getting a bit old. But this student particularly did a lot of experimentation. These were his findings when he was doing it. He discovered that if spaghetti is wet and then let dry, it shrinks, which can then distort it if it's already in position, or it might throw your bridge design off a little bit. It needs to dry evenly for fairly obvious reasons. He discovered that try and use the spaghetti from the same packet. So each packet, typical spaghetti packets are 500 grams. And because you only need about 230 to 250 grams of spaghetti for your bridge, you should be able to get it all from the same packet. Then you can hope that it's all from the same batch, which means it should be as even as possible. When you're storing it, keep the spaghetti with the bridge. It's just in the same conditions then, so same atmospheric conditions, it'll deteriorate or not in the same rates, which is what I said there. This is a bridge that was made a few years ago. It was unfortunately had to be disqualified. As you can see, there are holes in it, and then which can then be filled with glue, and so you can't use that type of spaghetti. Mike's mentioned this already, and I'm going to go through it in more detail in a minute. But just make sure the feet are longer than 35 centimeters, and that they're level. So the more level they are, the better it's going to sit on the rig, and the more evenly the forces are going to be distributed. Already talked about whether then don't use too much glue. I don't know if you can see my mouse or not, but you can see that this amount of glue here is fine. It's very difficult to minimize it, but we have had bridges in the past where it looks like they've just spray painted their whole bridge with glue, and that's sort of defeating the purpose. So of course you're going to have glue. There's going to be excess glue. There's nothing you can do about that. But as long as it's not obvious that all they've done is just hot dip their spaghetti bridge in a glue vat, then that's going to be fine. Yeah. All right. So this is what it looks like to test for those who haven't seen it before. This is the test rig. And you can sort of see down the bottom here, at the bottom is where the actual load cell is. We attach it to the bottom of the rig, and I'll show you some videos of that being tested shortly. So the load cell itself weighs around about half or just over half a kilo. And we have had plenty in the past where I hook the load cell up to the bottom of the bridge and the bridge collapses before we can even add any load to it. So if that happens, then we just give the students half a kilo and then we're good to go. Pardon me. In the past, we've given them 1 kilo, but that was being a bit generous because sometimes you can load it up and then it breaks at 0.8 and it's not really fair because at least they've had a load on it. So we leave that. We're going to make that 0.5 this year. Here's an example of a test, just so you can see it. So I'll run it through. Apologies if it's too loud. Just I can't do much about the volume, but just see how it goes. So we wind it up. The students do their own testing.
Keep going, keep going, keep going. Still taking strain, still taking strain.
Okay. Here's another test from a couple of years ago. This one is I think from memory was actually overweight. So this was higher than 300 grams, but we did, irrespective of whether it's overweight, I will test it. It just won't be eligible for any prizes. So if a student builds a bridge, they rock up and it's too heavy, that's fine. They can't be part of the competition in terms of the actual winning prize money, but I'll absolutely still test their bridge. They put the effort in, I'll still make an effort to test it for them. Sorry again about the volume. This one go. Now, that's a good example of what Mike was talking about there. Whoops. Yeah, so that was a good example where in the previous one, this one here, where the plate was not supported well enough. And so it just pulls straight through. And there's literally nothing we can do about that. So when Mike was talking earlier about supporting that load plate, that was the consequence of what happens when you don't do that. This was the winner from a couple of years ago now. And it's the highest that we've had in many, many years. So I thought I'd show you this one. Note what happens to the rig.
You're ready, mate. Just keep an eye on that weight of the scale as well. Is it working? Yeah. Cool. Ooh.
Yeah, so she goes quick when she goes. And as you can see from the bottom, that was 64 kilos of load with that bridge there. So that was an impressive piece of work.
You're ready, mate.
Ready. Yep, that's fine. So that's how it's tested. As you can see, it's pretty straightforward. We encourage the students to get heavily involved in their own testing. It's their bridge, so they find that a lot of fun. As you can see, maximum loads have changed over the years. For some reason in 2024, they weren't very high, which is perfectly fine, but they started to recover back into what is more likely. So somewhere between 50 and 70 is where we've been most years. But last year was actually, we had 42 and then I think it was 35 and then most bridges are from 12 kilos and down. So those results are available if you're keen and interested to find out. This year, we're very grateful that, as you can see, it's a significant increase in the number of locations where we can actually do live testing. You'll notice that one of them is this term at Lakes College in North Lakes. They run a tech fest there. And so if you have the capacity or would like to test your bridges earlier than term 3, then you're most welcome to do it then. Those bridges will just be added to the competition and it's not a separate thing. So I'll just keep all those results. And then our main testing time and the biggest event, we had over 200 students and teachers there last year, is our QT in Gardens Point, which is, pardon me, which is on August 10th, which is ECHA Week here in Brisbane. And then at my school on August the 12th and up in Townsville on August the 14th. That's a Friday. And then down to the Gold Coast and then up to Marsden on the 19th. That's a Wednesday from memory. And then up to Rocky on the 26th and then at the Sunny Coast on a Monday, the 31st. So the idea with that is if you're at a location near any of those, then you're most welcome to come to one of those. I'll provide specific details for each of those locations as soon as they become available, and then we'll update you as we go. The one in the Gold Coast is in the morning on that August, and the Marsden is in the afternoon. But other than that, those are our locations. Now, if you can't make it to any of those locations, they're too far away, or the time doesn't suit you, or you can't get time off school, or whatever it is, it's not a problem at all. So there's a couple of options there. You can, if you're in Brisbane and it's convenient, you can drop them off to one of those locations if it's close to you, and we'll test it for you on the day at that location. And then we record every test. So we video record and take photos of it, and then those videos are made available to you if you wish to see them after the competition ends. So if you can't do it live, you can't get the time off school or whatever, that's fine. We do encourage you though to bring some students along if at all possible, only because they put all the time into it. They want to actually see the outcomes of theirs, of what they've done for time. But if you can't make a location, then you can post or courier your bridge to us, and I will provide you with the address for that. And I will either test it at one of those locations, I'll take it with me, or I'll test it at home. And once again, the same will be applying. I'll record the test so you will see it, and I'll take photos of it so that you can then share that back with your students. So hopefully one of those times and locations is close to you. That's as much as I can do this year. I was hoping to be able to get up to Cairns, but that's just not going to be possible this year. So if there are any students or schools from Cairns or far North Queensland, please get in touch with me and we'll work out what the best option is for you. But that's where we're at the moment. So I'm really grateful to all of those teachers and schools for giving up some time and their location for me to be able to visit you and to test. And again, acknowledging QUT and their team in their STEM outreach program for allowing us to use their facilities there. The QUT Gardens Point will also have opportunities for the students to have a bit of a tour and have a look around and do some activities while they're there as well. So again, more information will come out to that early next term. Thanks to the Queensland Government and their sponsorship, we're able to offer, again, $2,000 in prize money. There's first, second and third place locations. And this year, the location winners, because I've got up to 8, I've had to reduce it a little bit. So what that means is per location. So if I go back one slide, so there are 8 locations here. So not including first, second or third. So if you're the best result bridge at one of those locations, at each of those locations, sorry. So if you're at Townsville State High School, for example, and your is the highest peak load bridge at that location, and you're not one of the first, second or third place getters overall, then your team will receive $75 as a prize money, which is split up amongst however many people are in your team. And obviously first place, second and third. And so we're really grateful for that, and that's very exciting. So even if you can't make it, if you are posting your bridge to us, I will include you in whichever. If you don't tell me where you want it to be tested, I will include you in the location closest to wherever it is your school. I've also had some students contact me. Do they have to register through their school? No, they don't. As long as, but they have to register using their school's name. That's all. Like some support if you need some help. There's some resources I can send you if you're interested. Some ideas. Our YouTube channel has some tests from the previous years, those videos that I showed you, and some others, so you can have a look. Students can have a look and see what worked and what didn't. Engineers Australia have some engineers that have volunteered their time to be a mentor. I've had one school already contact me and say, hey, can you put me in touch? I haven't done that yet, but I intend to this week. But yeah, if that's something that you are interested in, by all means reach out and let me know, and I will pass you on to the Engineers Outreach Program, and we'll get you in touch with a civil engineer who will either visit you or talk to you on a Zoom or Teams call or something like that. But that's an option if it's useful. Just let me know. All the information is on our website. Please don't hesitate to check it. Everything's there, including all the dates and times, the forms that you need to complete. There will be 2 forms that you need to complete from this point in time. One is actual register for the competition. So everyone's just so far done expressions of interest. They're interested in possibly being in it. I really need to find out where you want to test, and then a team registration. So who is actually in each of your teams will come a little bit later after that. So just keep an eye out for those, and that information will be emailed to you, put on our Facebook page, and also on our website. I'm just going to play this. These two gentlemen were from the Lakes College who won it 2 years ago. So I just thought I'd share this before we open up the forum.
Good morning, Jake and Thomas. Thank you very much for your time today. Congratulations on winning the Queensland Bridge competition for 2024. What made you enter the competition in the first place?
We both just kind of like engineering, like as a subject, and we thought it would be a good way to test our skills.
Cool.
And learn new things about bridges in a practical application.
Okay, so what sort of things did you learn that you didn't know before?
We learnt about different truss types, forces that go through trusses, bridge components.
And better ways to like just research in general as well.
Cool. Okay. Yeah. Did the competition in any way help shape your future career paths?
Yes.
In what way?
Well, now I'm more confident with bridges and engineering, and I've really got a go at making something at our scale, which is a confidence booster for the future, I guess.
Yeah.
Cool.
Yeah.
Good. And do you have any advice for any students who might want to participate in the competition in the future?
Lots of research.
Okay.
Plan your trusses. Yeah.
Great. Yeah. Thank you, gentlemen. Much appreciated. Congratulations again.
Thank you.
Okay. Bit of a shameless plug. One of our other events is the Engineering Link project. We had 240 students attend our event at QUT back in March. And then we're about to launch in the next week or so our Queensland tour for our regional tours. And these are the locations that will be in and when, which is the September school holidays. Around Queensland. So information will be coming out about those. So if you have students in those areas or near them, keep an eye out for that information. We're very excited to partner with Suki University and Queensland Government and Engineers Australia to offer that project, and we'll talk about that, and some details will come about that shortly. So I think that's enough from me, finally. Thank you for your patience. I will just again, I'd like to thank Mike and Natasha for their time, but I'll do that formally in a moment. But while we've got a few minutes left before we end at 4:30, or before, if there's no questions, does anyone have any questions that they'd like to ask either myself or Mike and Natasha? Feel free to unmute or type it in the chat, whatever works for you. Silence was the stern reply, which is, oh, no. Okay, so Catherine's asking any catastrophic design errors you've seen in the past. Oh, so many. I guess catastrophic is probably a lot. Typically, a catastrophic failure is when it's actually holding a lot of weight, as you saw from the one that won in 2023, because it took so much weight, or too much load, until it got to about 60 kilos. You could see the actual rig. That was a catastrophic failure. So if it's a catastrophic, it's typically going to be a good bridge. But the bridges that fail the quickest are the ones where the kids have just literally run out of time and they've just built a deck and there's nothing supporting that deck, is number one. But the most common failure is, as I showed you with that one, where the load hook just pulled straight through. So there wasn't enough support around the load hook plate, pardon me. And so because that load plate wasn't supported, it just pulls through. We do try and put it back in a different place and test it again, because we're actually trying to test their design structure, not the fact that they haven't supported that plate. But that's typically where it's going to happen. So yeah, that's the biggest error, is not supporting that load plate.
Yeah. Spaghetti is a brittle material, even once it's glued. So generally it'll hold the weight to a point and then it'll just break. So it's basically a catastrophic failure. If it's very thin, as you apply the load, it starts to bend, then it's not going to take much weight at all because it's already starting to essentially fail by bending because it'll just keep going.
Yeah, what will happen, particularly if students use a lot of glue, because what then happens is the spaghetti becomes flexible because the glue's sort of stopping it snapping, and so once it's, as Mike said correctly, once it starts to bend, it's not taking any more load, therefore that it's reached its peak load. So we'll keep testing it because it's more fun for the kids to actually see it fail and break and whatever. But once that bridge starts to bend like that, it doesn't take any more load and we've reached that peak, and then we'll stop. We'll either test it to its end, but we've already recorded that peak load. So they'll keep winding, but nothing's really happening on terms of the load. For those who want to come to a test event, you're not actually there for very long, to be honest. The QUT one goes for ages, but that's because there's so many bridges to test. Last year, I think we tested 80 bridges on the day, so it was huge. But for your particular school, if you come to one of the smaller events, you might be there for half an hour or 3/4 an hour. So it's not a huge amount of time. But so what we try and do is get you in, get the students testing. You can watch the other students and other schools that are there, if there are any other schools and that are being tested, and you can chuff off back to your own school. I do have a CARA, a curriculum and risk assessment, curriculum activity risk assessment that I can send you. So if that helps with your paperwork, I've got that ready to go, and I'll just flick that as an email, and you can include that when you're developing your risk assessments for any excursions or any visits you need to do. That's very simple. So just email me and let me know if that's what you'd like. Well, if there are no other questions, I just want to again thank Mike and Natasha, Mike particularly, for presenting today, for putting his time into preparing that presentation. Once again, mate, very much appreciated. Thank you to everybody who is on the call. Really appreciate your time. And thank you so much for taking the time this afternoon. I know it's week 4 of term 2. It's a nightmare, but I'm very grateful. Probably by middle of next week, this presentation will be up on the website. I'm away this weekend, so it won't be till then. But I will email you and let you know when it's there, and you can then access it as often as you choose. Otherwise, enjoy your afternoon. And again, thank you very much and best of luck in the competition, people.